Hello everyone and welcome to this next lecture in the NPTEL course Machine Learning for Core Engineering Disciplines. In the last class we looked at the support vector machine model for machine learning, whereby you could do both classification as well as regression by working with hyperplanes. So we were interested in either the best hyperplane that finds a separable point for two different classes, or it can model a part of the feature space wherein you want to predict the value of a continuous target variable. And especially one thing to note in the support vector machine model was the use of a kernel function, and this kernel function allowed us to bring non-linearity into the problem. So that was very interesting. Now leveraging the concept of a kernel function, we can also work with other machine learning models, and one of them is called kernel ridge regression, KRR. So in today's lecture we will learn about kernel ridge regression. So we will go back to ridge regression and then we will see how a kernel function can be introduced into it, and this will also give a segue to other non-parametric machine learning models like Gaussian process regression, wherein also you do use a kernel function to model the covariance of the variables. So let us go ahead and get started with kernel ridge regression. The topic for today is kernel ridge regression. KRR, and we are trying to build over the concept of ridge regression which we had introduced many lectures ago. So what was ridge regression? So if you recall, ridge regression was essentially linear regression using the sum of squared errors SSE loss function with a penalty term preventing the weights from taking excessively high values. Okay. So this is what was there in kernel ridge regression. So essentially we are trying to minimize the loss function subject to your weights and the bias beta naught, and we were minimizing the error between the true values y and the predicted values, which is x beta plus beta naught. So x is the data matrix and then you do norm squared, so that represents the sum of squared errors, plus there was a regularization term which involved the sum of squares of the weights, right. So this lambda is the regularization parameter. So if lambda is 0, you go back to linear regression, and higher the value of lambda, that means more penalty you are having on the sum of squares of the weights. And for the sake of completeness, this is the vector of true values and this here are the predicted values. And we wanted to find the optimal values of the weights and the biases. Okay. So that is what was going on in ridge regression, and in fact there was an analytical solution very similar to plain vanilla linear regression, and we said that this beta hat is essentially x transpose x plus lambda I inverse x transpose y, and here of course I am assuming that this X matrix also has a column of 1s, right, a feature that is 1 for all data points. So that will account for this constant term beta naught here, right. So, you can change the data matrix accordingly to add a constant into the model by having a vector of 1s, right, a 1 for every data point. Okay, so this was the analytical solution. Now what we will do in kernel ridge regression, right, in its simplest form, but there is of course more complex ways of doing this, we will introduce a nonlinear function, right, to transform the features, right. So using a nonlinear function phi of x, right, one applies a transformation on the features. Okay. So, your prediction y hat, which is f of x, so we are trying to approximate a function, is essentially beta transpose times phi of x, right. So earlier this is without the constant term, so I am not writing the constant term, but if you recall in linear regression without a kernel there is no linear transformation. So your y hat is simply beta transpose x, right, and x of course here is a vector of features and beta transpose is the vector of the weights. Now even here phi of x is a vector of transformed features. So you have applied a nonlinear transformation to each of the features and that is how you get this phi vector, right. So therefore we can write the optimization problem slightly differently. So what we had written above, the optimization problem now becomes so you will have minimization, right, of the loss function to find the weights and biases of the sum of squared errors loss function. So each true value yi minus beta transpose phi of xi, and if you want you can also add the constant term here, or if you do not have you can exclude it. So this is the sum of squared errors and then there is a regularization of the weights used here. If you want to write this in a slightly simpler form using vectors notation, then you can write it as minimization of the loss function with respect to the weights and biases beta and beta naught of a matrix phi multiplied by beta plus of course beta naught if you have a constant minus y, right, norm squared plus lambda norm squared of beta. So now what is this capital phi matrix? Okay. So if you recall here we had a capital X matrix and now we are saying a capital phi matrix. So one can guess that this capital phi matrix, right, capital phi is essentially a matrix where each feature, right, value xij. So xij means the jth feature in the ith data point. So jth feature in ith data point is replaced by the function small phi that I had introduced here applied on xij. Okay. So the ijth entry in the matrix capital phi is basically the small function phi applied on xij, right. So now what are some examples of this nonlinear function phi of xij? It could be something like phi of x is x to the power p, right, and p could even be 1. So, then it goes back to a linear problem. Okay. So, this is only the most simplest form of kernel ridge regression, wherein you interpret what is happening as a nonlinear transformation of the features, right. However, in its more general form, KRR is very flexible, right. It involves the use of a kernel function, right. So, you no longer talk only about transforming one particular feature, right, by this nonlinear function, but you start talking about a kernel which applies to 2 points taken at once, right, and this was what also happened in support vector machine. The kernel always talks about some kind of an inner product or a function of an inner product of 2 different data points. Okay. So, in the most general form, one works with a kernel function. That is why the name is kernel ridge regression, and this kernel function is similar to what was happening in support vector machine, and this kernel function is related to this phi matrix multiplied by its own transpose, and we will see why that is the case, right. And this kernel function small k defines the kernel matrix. Capital K. Okay. So, now capital Kij, so the entries of the kernel matrix are the small k's applied on data point xi and data point xj. So, the ith and the jth data points. So, to explain the notation here, this is a nonlinear kernel function and xi is the feature vector of the ith data point. Okay. And this kernel matrix is related to the phi matrix that we had defined. It is actually related to phi transpose. Okay. When you have a simple kernel like this, but like I said that overall the kernel matrix can even be defined when your kernel is not separable, when you can't write it as some function of data point I multiplied by some function of data point j, right. In this case you can, right, because if you take data point I, it will be xi and data point j will be xj. So, then you can write it as the product of some function applied to the 2 values, but in the more general case you can't write it like that. So, let us see what happens in those cases, right. So, some examples of course to give you a feel for what is happening, and you have seen these examples even in support vector machine with a kernel. So, you could have a polynomial kernel where your Kij, right, ijth entry of the kernel matrix is 1 plus the inner product of the ith and the jth feature vectors to the power d. Okay. And then you also had this RBF kernel, radial basis function kernel or the Gaussian kernel, and this kernel is Kij equals exponential of minus the norm squared of xi minus xj. So, essentially the distance squared between xi minus xj divided by 2 sigma squared, and there is like I said a minus sign before, right. So, these are some of the kernels used, right. So, now in this case, right, now let us go back to this problem here, right. So, this was the problem we had defined. Now, for this problem you can write the analytical solution. So, earlier the analytical solution was x transpose x plus lambda I inverse x transpose y, and now we are saying that this X is simply being replaced by the phi matrix, right, capital phi matrix. So, you can easily guess that the solution will be phi transpose phi plus lambda I inverse phi transpose y. Okay. So, the optimal solution in KRR, in kernel ridge regression, for the weights is given as beta hat equals phi transpose phi plus lambda I inverse phi transpose capital Y, right. Now, so far everything seems like it is just like linear regression, but this is where all the novelty happens, whereby you are able to introduce non-separable kernels like this, right, functions which can't just be written as products of some function applied on the ith data point, features of the ith data point and features of the jth data point. So, there is something different we will do here, and at the heart of this is an identity that can be proved in linear algebra. So, it can be shown, and we will not prove it, but we will verify it, that your phi transpose phi plus lambda I, and here the identity matrix is of size p by p. You can confirm that because phi is of the size n by p. So, phi transpose is of the size p by n. So, phi transpose phi is of size p by p. So, that is phi, we need I of size p by p times phi transpose. This can be shown to be equal to capital phi transpose phi transpose plus lambda I n inverse. Okay. And if you remember what we had said, this is essentially the kernel matrix K. Okay. Now, why are we doing this? We are doing this because there is a really nice physical interpretation of what can be done if you assume this, and mind you, you can check that this identity is correct. So, how do you check this? So, if you want to check this, you simply multiply both sides by whatever is there on the right, okay, this term here. Let us multiply both sides by phi transpose plus lambda I n. Okay. So, after you multiply, what is the left hand side? So, once you multiply by this, the left hand side will become phi transpose phi plus lambda I p inverse phi transpose multiplied by phi transpose plus lambda I n. Okay. So, you can now work through this, you can multiply the second and the third terms here. So, the first term remains whatever it was, but you can take this inside and this becomes phi transpose phi transpose plus lambda, which is essentially a scalar, times phi transpose I n. Okay. Now, this can be further simplified. So, this becomes phi transpose phi plus lambda I p inverse times phi transpose phi transpose plus, now if you take a matrix and multiply it by the identity matrix, right, of the appropriate size, then you recover the original matrix. So, this just becomes lambda phi transpose. Okay. So, now what we do something that will really help us, we plug these phi transposes, we pull these phi transposes out of this expression, right. You remember we had multiplied the phi matrix into this. Now, that was the phi transpose which appeared first. Now, we are taking the phi transpose which appeared last and we are pulling it out of this term. So, what do we get? We get phi transpose phi plus lambda I p inverse times phi transpose phi plus, now you will get actually lambda I p here, right, because the dimensionality has changed. So, this should be lambda I p, and you can check that the dimensions are consistent and you have taken phi transpose out. Okay. Now look at this here, something really nice has happened. You have an inverse of the matrix here and then you have the same matrix here, okay, and these are square matrices. So the inverses are actually defined. So this just becomes the identity of size p multiplied by phi transpose, and of course that is just phi transpose. So the LHS upon multiplying by phi transpose phi plus lambda I n is just phi transpose. Now what about the right hand side? So if you take the right hand side, that was just phi transpose multiplied by this inverse and we are multiplying by this same quantity here. So the RHS upon multiplication is simply phi transpose. So what we have shown here is that two matrices are equal once we multiply them by an equal matrix. So those matrices should have been equal even earlier. So that means that this particular expression on the left is equal to the expression on the right. Okay, so we have not strictly proved it, but we have at least verified it in this lecture. Okay. So now you will ask, I mean, why are we doing this? What is the benefit of doing this? And the benefit of doing this is to introduce arbitrary kernels into the picture. Okay. Now we have shown that this optimal solution in the kernel ridge regression, instead of writing in terms of phi transpose phi plus lambda I inverse, you can write it in terms of this here, okay, this whole expression. So whatever is there on the left hand side, right, this whole thing you will replace with what is there on the right hand side. So let us go ahead and see what happens when you do that. So thus the optimal set of parameters in kernel ridge regression becomes the following. So beta hat therefore becomes whatever was on the right hand side, this quantity, right. This is phi transpose phi transpose plus lambda I n inverse multiplied by y. Okay. So we have gone from this expression here wherein we plugged this whole thing to be this here. Okay. So I hope you understand how we got this expression. Now this equation we have written here has a really nice interpretation, okay, and the interpretation is as follows. So this here phi transpose is a matrix of size p by n, and this whole thing here is actually a vector of size n by 1. Now there is a nice thing in linear algebra which says that matrix vector multiplication, which is what is happening above, this can be viewed, and you will have to take a linear algebra course to understand this, or you can try to work out through it on your own. So matrix vector multiplication can be viewed as a weighted sum of the columns of the matrix with the weights specified by the entries of the vector. So essentially you are doing a weighted sum of the columns of this matrix by the weights being the entries of this vector. Okay. So we can write this expression in a really nice way now. So let us assume, let us denote that this alpha here to be this particular vector here. So let alpha be phi transpose plus lambda I n inverse y. So, this is a column vector, right, and let its entries be alpha I. So, what we are saying is that beta hat is some I going from 1 to n. So, it is a linear combination of the columns of the matrix, right, with the weight specified by the entries of the vector. So, alpha I times the columns of the phi matrix, phi transpose matrix. Okay. So, this capital phi I am writing here, this is essentially a column vector with the function psi, sorry, function lowercase phi applied to every feature of data point I. So, this is very interesting. What we have shown is that the optimal set of features is a linear sum, right, over all the data points in the training set, right. So, we have uncovered the relationship between the optimal set of parameters and each point in the data set, how each point contributes to beta hat, right. So, this is what we have done here, and now even more interesting is what will happen if you try to predict a new unseen data point. So, the prediction of an unseen data point can now be given as y hat is phi transpose x times beta hat. Okay. So, it is the inner product between the transformed features and your optimal set of parameters, and let us plug in beta hat here. So, this becomes phi transpose x times sum I going from 1 to n phi of x, and this becomes some I going from 1 to n alpha I, yeah, I had missed the alpha I there. So, alpha I times phi transpose x I times phi transpose x, yeah, x phi transpose x times phi transpose x I. Okay. So, this is really nice, right, because now what we are claiming is that the prediction of a new unseen data points is simply given as a contribution, right, of a weighted contribution from every point in the training set. So, every point in the training set is accounted here. Okay. The other interesting thing which has happened because we wrote kernel ridge regression in this manner is this is essentially an inner product, and if you remember what we had done with support vector machines, whenever you have an inner product you can actually introduce a kernel function. Okay. So, your y hat becomes some I going from 1 to n alpha I times the inner product of capital phi of x comma capital phi of x I, and this more generally can be written in terms of a nonlinear kernel function. So, some I going from 1 to n alpha I times a kernel function k that works on x and xi, right. So, we have replaced the inner product by a kernel function and these can be the polynomial kernel or the radial basis function RBF kernel that I had introduced a little while ago, and you had also seen in the lecture on the support vector machines. Okay. So this is beautiful because there are two things that have happened here. The first is that your prediction for a new point is a weighted sum over the training data. Okay. And second is essentially through this kernel function you are trying to account for some kind of similarity between the points, right, so that the prediction can be physically interpreted as depending on how similar the features of the new point x are to features of existing points xi in the training set. Okay. So this is really interesting, and I just want to remind you that we already know what alpha I is. So alpha I is not an unknown, we actually had an analytical solution for this. So alpha I, right, is obtained from as before, right. So what was alpha I? So your alpha I was given by the entries in the vector. Alpha, that was phi transpose plus lambda I n inverse y. Okay. Now when you only talked about capital phi as the matrix of features with the nonlinear function lowercase phi applied, then it was fine, but now when you replace this inner product by a kernel function, obviously we have to make some changes in alpha as well. So like I had said earlier a little while ago, this phi transpose is interpreted as the kernel matrix, which is denoted as capital K. So then the ijth entry of the kernel matrix is essentially a kernel function, right, applied on xi and xj. So the features of the ith and the jth points, right. So if you are not using this phi to be just depending non-linearly on one function, but instead you want to use these non-separable kernels, then you have to work with the kernel matrix where each entry can be calculated as this, and then your alpha I, right, are the entries in alpha equals k plus lambda I n inverse y. Okay. So this is how you will obtain the alpha. So it involves the kernel matrix. The kernel matrix comes from the training data. So this is the kernel matrix which appears from the training data. That kernel matrix is used to obtain the weights alpha, and then you can sum over the weights alpha and the kernel function to get the prediction on a new point x. Okay. So this is the gist of the kernel ridge regression method, right. So I hope you now have come to appreciate how the KRR method works. It not only applies to situations where you use separable kernels, right, wherein you just talk about a nonlinear function lowercase phi which transforms all your features. So that is one way of interpreting that, but the other way of interpreting more generally is to introduce a kernel matrix which tries to encode the similarity between two different data points, and thereby the prediction for a new data point depends on how similar that new data point is to existing points in the training data set, right. So with this understanding we have completed our study of kernel ridge regression. I hope you learned something new today, and I look forward to seeing you next time, wherein we will discuss the principles of Gaussian process regression, which is a Bayesian approach to machine learning. Thank you, and I look forward to seeing you next time.